And good morning, everyone. Today I'm gonna start a new chapter 7, rotational motion, and you will see this is nothing but the same concept that you learned last chapter. And the chapter 2, that was about one-dimensional and two-dimensional kinematics, right? But this is a rotational version of kinematics. Okay? So first, in order to describe circular motion, we start with angular position, which is very similar with the linear position. So in general, linear position, which is delta x, right? So the first concept you learn in chapter 1 is about the displacement, which is a delta x. So which is a x final minus x initial, right? Your final position minus your initial position. But angular motion, basically we are talking about the angular motion for circular motion, which means if you have a circle and then we assume the object is moving along this circumference. Okay. And then angular position is basically angle changes over time. So for example, if your particle is here, which is on the circumference of this big circle, right? So then your position, which is a angular position here for this case, is described by the angle theta, which is measured from the positive x-axis. So this corresponds, you see, your x corresponds to angle theta, right? So the angle theta is an angular, in other words, it's a called angular position of the particle. And again, theta is positive when measured counterclockwise from the positive x-axis. If it is measured from the clockwise, so in other words, let's assume you have a particle right here, and that means your angle here, you can either measure it from here to here, so which corresponds to this angle, or you can simply say minus this angle as well. Okay. And then from now on, we're not gonna use degrees. We will use radians. Okay, and then very important, and the very first equation starting, this is circular motion, is the relationship between the radius r, angle theta, and arc length s. So s is a arc length, s is a r theta. This is only true when the theta is a radian. For example, if you think about one full circumference of a circle whose radius is r, what is the arc length? That is the circumference, which is a 2 pi r, right? So then, if you think about one full revolution, r is r, what is your theta? So that means that the angle which corresponds to 360 degrees, which is a 2 pi. So that is the arc length with the angle 2 pi. Again, the theta must be radian, right? Okay, so we have a new equation. S arc length is a r theta. This is the very first equation you have to remember for any circular motion. This is extremely important because we will use this formula over and over. Sometimes instead of a s arc length, because this is a length, we can sometimes say this is a x as well. Okay, so then this is the relationship, or theta is a s over r, or s arc length is a r theta. Again, you can sometimes call this a x linear displacement. So then again, if this is the angle of a full circle is a 2 pi radian, of course, as you might know, right? So 360 degrees are 2 pi radian. In other words, 1 radian is roughly 50 cent 7 degrees. I believe most of you already know. Okay. And now, So far, we talk about angular position, which corresponds to x. And the next one is the angular displacement. So far, we have a theta corresponding to x. And then now we are talking about angular displacement, which is a delta theta. So of course, this corresponds to delta x, right? Where delta x is what? X final minus x initial, right? So for unit for motion, you see here, this is let's say this is 1, 2, 3, 4. Then this is a 4 meter. This is a 3 meter. Your delta x for this case is a 4 minus 3, so 1 meter, right? So likewise, you have the same concept. Delta theta is the angle, right? So for example, let's say you have a circle, and then this is your theta initial. So then it's a roughly 45 degrees, which is a pi over 4. And then now your data is changed by this much. So this is a data final, which is a pi over 2. So what is your delta theta from, delta theta from here to here? That is a pi over 2 minus a pi over 4. In other words, this is the theta final minus the theta initial. So that means this is also pi over 4 as well, right? So this is again 45 degrees, right? So the concept is exactly same as delta x, right? So definition here, delta theta is a theta final, the final angular position minus the theta initial angular position, like you did for displacement. And the next concept is angular velocity. So now, so far, we have a theta corresponds to x, and then we have a delta theta, which is a theta final minus a theta initial, right? And then this corresponds to delta x, which is what? X final minus x initial. And then now next concept is omega, which is called angular velocity. And then this corresponds to velocity of the linear motion. And then everybody remember the definition of velocity, which is a delta x over delta t. So now your omega is a delta x corresponds to delta theta. So this is the delta theta over delta t. So this is actually angular velocity, meaning it's an angle changes over time, right? And if this is a uniform circular motion, that means that the angular velocity is constant. Then angular velocity is a constant for a particle moving with a uniform circular motion. So the angular velocity, omega's concept, is exactly same as the concept for linear velocity. The only difference is here is instead of a delta x, you have a delta theta. Right? So for example, let's find the angular velocity of the particle here. So for example, you have a initially here, and then you have final velocities here, right? And then your omega angular velocity is again delta theta over delta t. So then now you see the delta t from here to here is 1 second. And then how much angle changes you have? 1, 2, 3, 4, 5, right? So then basically this angle from here to here is what? Pi over 2. But now you have a 20% of it, right? So 1/5, right? So this is a 1/5 of it, right? So this is actually pi over 10. That's the angle change delta theta, right? So you have a pi over 10. So you have a pi over 10 radian per second. So the unit for the angular velocity, what is the unit for the linear velocity? V is a meter per second because this is the displacement divided by time. Likewise, omega unit, instead of a meter, we have an angle radian. So its unit is a radian per second. Right? So this is the speed, angular velocity of this motion. And then we'll do the same thing for here, but now in the second one is a 10 over pi, right? And then second one, you see, you basically move this much angle changes. So this angle is basically 1, 2, 3, 4, 5 over what? Pi, right? So the angle from here to here is a pi radian, and then that's the fifth of it, right? 20% of it. So the angle change is a pi over pi, right? And then time is 1 second, so divided by 1 second. So that is your angular velocity for the second case, right? And then you see the first velocity is exactly half of a second velocity. Think about why? Because every second, for the first 5 seconds, your angle changes will be pi over 2. But second case, during the same time, 5 seconds, your angle changes is a pi radian, right? Which is a 2 times greater. So of course, angular velocity is gotta be 2 times greater than the first one. So then again, because of linear displacement, so this one, if I rewrite it, your Vx is gonna be what? Delta x over delta t. So in other words, this is a x final minus x initial over delta t, right? So this is nothing but, this is nothing but, the same, right? So then now you have the same relationship, right? So angle change, of course, is a velocity times a time, right? So in other words, your displacement, distance your displacement is a velocity times the time. So you see, everything is the same, except you simply switch delta x to delta theta, and then v to omega. That's it, right? So except these, variable changes, everything is exactly same as chapter 2 for circular motion, right? And then another definition of angular velocity is very important. So last time we talked about the frequency and period. Everybody remember, right? So let me quickly remind what we did last time. So assuming we have a circular motion starting from here, and then let's assume you complete one full cycle, and it takes a time period t, right? That's the definition of a period, right? How long will it take to complete one cycle or one full revolution motion, right? And then the frequency concept is what? Frequency is how many cycles you complete in a second, right? So the relationship between T and F is what? T is 1 over F, or F is 1 over T, right? So that's what we did the last time. But now, let's think about the definition of omega. Definition of omega is that the angle changes over time changes, right? So that means let's think about one full evolution of the motion. So this is the when you have a displacement change by amount of theta. But now let's assume, what if your theta is 2 pi radian, which means you complete one full evolution. Then your angle change will be 2 pi radian, right? Because again, this is 160 degrees, which is a 2 pi radian. And then the time for one full evolution is simply what? Period t, right? So then another definition, or you can say this is not a definition, this is a one example of this case, one full evolution, right? So your omega, you can also find your omega by using this formula, 2 pi over t. So again, because 1 over t is a frequency, you can also say omega is a 2 pi radian times a frequency. So basically now we have a one more family member here. We know t, we know f, right? If we know t, for example, you know f, right? Or if you know frequency, you can find the period as well. But because of this equation, if you know t, you can find the omega as well. So that means if you know t, f, or omega, one of these, you can find the other two automatically mathematical. Right? Which means even though these three has a different physical meaning, again, period, the time to complete one cycle, frequency, number of cycles per second, angular velocity, omega is the d theta over dt. But even though they have different physical meanings, mathematically, if you know one of them, you know the other two. Right? So this is the final punchline. If you have as the position x for linear motion corresponds to theta for circular motion. If you know velocity, which is a dx over d theta, you can find the omega, which is a d theta over dt. And then one more thing here is acceleration. Your acceleration is nothing but what? Velocity changes over time. So you can also define angular acceleration, which is angular velocity divided by time. So then you see, if you compare linear motion with the circular motion, basically you see everything's are the same. So the five kinematic equation you learned in chapter 2 are the same as well. Except that you change x to theta, you change velocity to omega, and you change acceleration, linear acceleration to alpha, which is a angular acceleration. Then your equation for kinematics are exactly the same as a linear motion. So a ball rolls around the circular track with the angular velocity 4 pi radian per second. What is the period? Again, think about the relationship omega. Your definition is the fundamental definition of omega is the d theta over dt. But if you again think about one full revolution of this circular motion, the angle change is gonna be 2 pi. And then how much time you need to complete one cycle. That's the definition of a period, right? And then, because one of our period is a f frequency, so you can say this is a 2 pi f. Again, the very important concept here is if omega t or frequency, if one of them are given, you always can find the other two. Right? For example, this case, your omega is given. So that means your omega here is a 4 pi. So which is 2 pi over t. So then now you see the t must be, so then 4 pi equals 2 pi over t. So your t will be 2 pi over 4 pi. So this is a 1/2 second. So your answer is a A. But if you're asked to find the frequency as well, you can find the frequency, right? Because why? Your frequency is a 1 over t, so 1 over 1/2, which is a 2 hertz. So you can also find your frequency. Again, the key idea is if you know one of these three, you find the other two. A crankshaft in your car engine is turning 3000 RPM. Again, so that last time we talked about one more family member, right? So last time we talked about period equals 1 over frequency, right? So that means, if we know one of these two, you know the other one, and then here we add, today we add one more family member. But remember we had one more family member last time, right? Which is the RPM, right? So RPM is what? Nothing but revolution per minute, right? So what is the concept of frequency? Revolution per second, right? So revolution per minute. So that means 3,000 revolution per minute means 60 seconds. So then if you simply change denominator from 1 minute, basically it was a 3,000 revolution per minute, right? But now 1 minute is a 60 seconds. So if you switch your unit from minute to second, this is a 50 revolution per second. So then what is the concept of this one? revolution per second. How many revolution per second you have? That's exactly the concept of a frequency, right? So then you can add one more family member here, which is a RPM. So in other words, if you know RPM, you know the frequency. So that means if you know frequency again, you can find the period, you can find the angular velocity as well. So if you know, in other words, if you know one of these four, you know the other three, right? So for example, here, our RPM was a 3000. So now you can immediately convert 3000 RPM is what? 50 hertz frequency. So then now your F is a 50 hertz. So that means your omega is what? Delta theta over delta t is gonna be 2 pi over t is gonna be 2 pi f, right? So then 2 pi times a 50, 2 pi times a 50, which is a 314 radian per second. That's your angular velocity. So again, now we have a one more family member, T, F, RPM, and omega. If you know one of these four, you know you can find the other three. And then, so everything same. So now, if you have so remember the linear function. So in general, you have a x t graph, right? So in x t graph, the slope in x t graph was what? Your velocity. Why? Because the slope here is gonna be delta x over delta t, right? So which is a rise over run, right? So that's the definition of velocity. So then everything same now except you switch this x-axis to theta. Then the slope will be delta theta over delta t. So that's gonna be angular velocity, which is a omega. So the slope of a theta t graph is gonna be your angular velocity, right? So for example, your angular velocity, you can find the slope of this line, right? So for example, you can choose, this point, for example, your height here is a 2 pi, and then your run is a 0.6. So that's your angular velocity for this motion, right? So concept, again, the same. So theta t graph concept is exactly same as a x t graph of a linear motion. And then another important thing here is, think about the very first equation I introduced when I started this chapter. What was it? X equal r theta, right? So then now let me summarize what we have done so far. So we start with the x equal r theta, or sometimes we say this is arc length s, but I prefer to use x. You'll see why. And then here, what do we have? We have a omega definition is a delta theta over delta t, or 2 pi over t, and then this is a 2 pi f, right? So this is all we have done so far, right? And then plus what? RPM, which is another member of this board, right? And then now, if you divide this equation both sides by delta t, so then displacement over time is gotta be velocity, right? So so let me write down. So your x over t equals r theta over t, right? So I simply divide this one both sides by t. So then what is this? Yeah, this is nothing but velocity. And then how about this? Theta over t is your omega. So this is r omega. So in other words, your velocity is a radius times a omega. So then now we have one additional family member, which is what? Your omega. If you know omega, this is a delta theta over delta t, which is a 2 pi over t which is a 2 pi f. And then you can also relate the frequency with the RPM, right? So that means omega t frequency and RPM, these four are the same family. In other words, again, if you know one of them, you can find the other three. But now, because of the x equal r theta, the fundamental equation for the arc length, if you divide both sides with the t, you will have a v equal omega r. So that means if you know omega, and then assuming we know the radius of the circular motion, you know the v as well. So then we have a one more family member, v. So in other words, if we know one of these five, we can find the other four, right? So this is a final family member, okay? So make sure if we know one of these four, one of these five, we can find the other four mathematical. So again, even though they have all different physical meaning, mathematically they are all equivalent. So for example, a large wind turbine, right, has three blades, you know, length is 50 meters, so that means your R is the 50, and then rotated at 10 RPM. So now you see one of the family member, which is a RPM. Again, if you know RPM, immediately now your idea is, okay, I can know V, I know V, omega, I know T, I know frequency. Okay, so then now you see the question, what angular speed V, right? So it's a angular speed. So this is basically asking you omega, right? What is the speed v of the tip of the blade? So you're looking for b. So this is even though they said call b, but this is basically omega, right? So basically you're looking for omega and the v, right? What is the speed of a radius 25 meter from the hub? So that's the next question we can talk about. So basically, you know, this question is very simple. When you know RPM, what is omega and B? So then now RPM is a revolution per minute. So that means it will have a 10 revolution per minute. So then if you convert this concept to frequency, in other words, how many revolution you have in a second. So again, 10 per 60 second. So your frequency is 1 over 6. So then now you know frequency is 1 over 6. Or it was originally, you can find it 10 over 60, right? From RPM information. So then you can find the T. What is T? T is 1 over F. So you see T is got to be 6 seconds. Once you know T, you can find your omega. What is your omega? Which is a 2 pi over T, which is a 6, right? So this is a pi over 3. Good. That's your omega. And then what is your V? V is a R omega. So where your R for point B, it says it's a radius is a 50 meters, right? So this is a R times omega was a pi over 3. That's your V. And then next question, the last question, what is the speed 25 meter from the hub? So then your V is now, this is I'll call V50, and I'll call this is a V25. So then same, R is a 25, your omega is a pi over 3. This is the answer. You see how simple every single questions are. Right? So again, the rule, this question, you're given RPM, and then you can find the TF omega B, right? That's it. Okay. And then the last part of, if you remember, so basically, linear motion, you have a xt graph, or you have a vt graph, or you have a acceleration versus a time graph. But this is what you have for the linear motion, right? And then the slope in xt graph will be velocity. The slope in vt graph will be your acceleration, right? And then what is the one additional information you have about the, in addition to this slope information? That is what? In VT graph, area under the curve will be your displacement, right? That's the only additional information, right? So then now you have a omega and then t. So then slope here will be angular acceleration, right? So this is an angular velocity graph of a wheel. How many revolutions does the wheel make in 4 seconds? So then how many revolutions? So basically you're looking for displacement, right? So the in 4 seconds, the area here is a 2 by 2 is a 4, and this is a half. So the total area here is a 6, which is your angular displacement. So the answer is a 6. Okay? So again, you see, if you understand chapter 2, kinematics completely, there's nothing new here. And then I'm going to talk about the rotation of a rigid body. So rigid body, every point on a rotating body has the same angular velocity. Think about why. Let's assume this is a rigid body, which means all points are rotating at the same time. So that means, okay, we are interested in, let's say, point 1 and then point 2. Those locations are different. But now, during the given time, point 1, moves from here to here, and then point 2 moves from here to here. And then what? So that means point 1 rotated by angle theta 1, and then point 2 by theta 2. But now you can obviously see angle theta 1, theta 2 are the same. So that means particle 1's angular velocity, which is a delta theta 1 over delta t, versus particle 2's angular velocity, which is a delta theta 2 over delta t. And then you see this is a omega 1, this is a omega 2. But now you see they are the same. Of course, why? Because they have the same angle change during the same given time, right? But the actual velocity of each point will be different. Why? Because object 1 travels from here to here, this short arc length, while object 2 travels this longer arc length during the same given time. So of course, object 2 will move faster. Why? Because this is simply v is r omega. For first one case, v1 equals r1 omega 1. v2 is r2 omega 2. But again, omega 1, omega 2 are the same, but r1 and r2 are different. Why? Because this is r1, this is r2. Okay? So then now we have two persons, Rashid and Sophia riding on a merry-go-round, right, spinning steadily. And the Sophia is twice far from the axis as the Rashid. Sophia angular velocity is what? So angular velocity. So let's assume, sometime later, maybe 1 second later, Sophia is here. And then where is our Rash? Here, right? So the angle change for both cases, they have the same angle changes and same time. So the answer is they have the same angular velocity. Okay? And then now the speed. So this is actually they are looking for the velocity. So then now we have a Vs versus a Vr, right? So Vs is a R omega, and then this is a, so I'll say R zeta Rs omega S. This is R omega R. But what we found from the previous question is what? Omega S and omega R are the same. So these two are the same. The only difference is RS and RR. So RR, let's say this is 1 meter, then this is gonna be 2 meter, 2 times longer. So the Sophia's velocity is 2 times faster, right? So the answer is C. And the same thing, you have two coins rotate on a turntable. Coin AB, coin B is twice as far from the axis as coin 1. So then angular velocity, of course, they are again the same, right? Angular velocity are the same. Linear velocity are 2 times faster for B, right? So angular acceleration definition is again same. So the linear, again, your delta x corresponds to delta theta. So if you divide by t both sides, that's your velocity. And then this is a angular velocity. And then if you divide both sides by another t, you see this is going to be acceleration. And then this is also angular acceleration. And the definition of angular acceleration is again delta omega over delta t, which is very similar with the delta v over delta t, right? And then because angular acceleration is also vector, we define when the angular acceleration direction is a counterclockwise, that's a positive. So for example, non-zero angular acceleration, what does that mean? Your angular velocity, delta omega, is a non-zero, right? So that means your angular velocity is changing as a function of time. So for example, okay, for the first second, I move this much. And the next second, I move more angle. And then I'll move more, right? So the angle is getting bigger and bigger during the same given time. So that means your omega here and then omega here are different, right? So for example, your omega gets faster and faster, right? Compared with the first second, right? So that means your omega is not constant. So that means your acceleration, angular acceleration, is a non-zero, right? And then alpha is positive when the rigid body is rotating counterclockwise and speeding up. Think about why. So in order to speed up, right? Initially rotating, counterclockwise uphill, which direction of a force you have to apply? You have to apply force counterclockwise as well. So then this is why this is a positive angular acceleration. But even when the wheel is rotating clockwise but slowing down, so that means which direction of a force you have to apply. You also have to apply force in this direction, right? So both cases you need the same direction of the force, which means the acceleration is a angular acceleration is a positive. But the opposite case here, the object is moving, rotating counterclockwise, but now it's slowing down. So that means which direction of force you need. You have to apply this direction of force, right? So that means your acceleration, angular acceleration, is a clockwise. So that means that's a negative. Same thing. If your object is rotating clockwise and speeding up, so that means which direction of force you have to apply. You have to apply this direction of force, which is the same as this case. And your force direction is again clockwise. So your angular acceleration is a negative. So this concept is exactly the same as what we did in chapter 2 when we determined the sign of the linear acceleration, right? So if you make sure you go over chapter 2 with this part, we had a lot of examples for discussion, okay? So then now a fan blade is slowing down when it's rotating clockwise. So in order to slow down rotating clockwise fan, which direction of force you need? You have to apply this direction of a force, right? For this case, sine of the omega, because omega itself is rotating, this fan is rotating clockwise, so your omega is a negative. But you have to apply force counterclockwise, so your alpha is a positive. So the answer is a C, right? Another case of fan is slowing down when it's moving. Oh, sorry, this is the same question, right? So, yeah, I think this is the, yeah, so let me change the final question. So now let's say this is speeding up. So the fan blade is speeding up this way when it's rotating, right? So then again, what is the sign of omega? Omega is because of the pan direction, rotating direction is, clockwise. So again, your omega is negative. But this time I assume the fan is speeding up. So this fan is getting faster and faster. So that means which direction of force you need. You have to apply your force to this direction as well. So that means your alpha is a negative as well. So that means in this case, your answer will be D. Okay. So again, I upload the exam today, so which is due tonight. So make sure you complete your exam and then submit it and upload it in Canvas. And I'll see you again. Thank you. If you have any question, please let me know.